to go ahead and welcome everybody. Thank you very much for coming to this thesis event. So this is going to be a defense of the thesis entitled High Power Cyclotrons, the bridge between beyond standard model physics, computation, and medical application. And it will be by Loyd. Everybody's here. And I always have an introduction that tries to give people the flavor of the student and what the student has accomplished. And I think this time, actually, a better way to do it than just having me talk about who Loyd is. I want to share something with you because I thought it was really neat and really fun. Okay, so let me just get rid of this. Not even say that. There we go. And so Loyd has had to deal with me asking him to do lots of talks. In fact, I often am like, here are 5 talks we have to do by Zoom, and you get to do them all. Isn't that right? How many talks did you give them last week?
This is going to be number 6, I think.
Right.
Yeah.
Out of that, it's how to communicate really, really well. And so he actually won 2nd place in the TED Talks Particle Accelerator Physics competition. And this is what he won with. And I really feel like this is actually a great introduction to also not only Loyd's physics, but who he is.
In the standard model, there are 3 different types of one for each dilemma. In 2015, the Nobel Prize was awarded for showing neutrino oscillations, so that neutrinos can change their flavor. Well, some experiments have found anomalous behavior of these neutrino oscillations in multiple different channels. The explanation? A theoretical particle. Heavier, which is not interacting with those visible star detectors, the so-called sterile neutrino. In fact, theoretical models with new evidence point to sometimes several of these sterile neutrinos, not just a single one. But if you want to confirm these neutrino anomalies definitively, you can't just have a couple of neutrinos. You need to have a bunch. So that, or isotope. To make all these neutrinos, we irradiate a target with high power proton. This provides high enough statistics to definitively evaluate these anomalies, as well as evaluate several additional models with more than one sterile. But to make a high power neutrino source, you need a high power proton source. Not only that, but it needs to be compact. Constructed near a large neutrino detector, which to avoid cosmic, is typically built underground. So we're designing a new type of cyclotron that is actually 10 times higher current than what's commercially available. The isotope cyclotron. How are we going to do this? Well, we're taking 3 breakthroughs to higher current. First, we replace the common H- and proton beams with an H2+. Here's our lab. I've been working with the design and commissioning of a new ion source to give 2 units of current for the price of 1. This way, we limit space charge and emittance growth in our beam. Next, I've designed a transfer line connected to a radio frequency quadrupole direct injection system. This system works with bunch of these to dramatically increase end-to-end transmission. Lastly, we utilize the vortex motion effect, or rather than propelling like a beam with low space charge, the beam actually curls up on itself, allowing for higher time separation, cleaner beam extraction. To take advantage of these effects, which is complex parameter spaces, and train machine learning models to optimize our design. Putting all this together, we have worked to design isotope cyclotron. Here's where it gets really interesting. The isotope experiment is just about the neutrino. I've shown the nuclear reactions to the isotope target actually produce theoretical dark matter particles called Axion. Not only that, the high power of the isotope cyclotron can make medical isotopes orders of magnitude more portable by producing large amounts of currently rare nuclear medicine treatments. So the isotope project is a broad and fascinating project. It's a clear example of experiment that shows that there's a direct connection between technology that can not only help us understand our universe, but also save people's lives.
That's it. That was the defense. Actually, it's a pretty good description of what's going to happen in the defense, for sure.
Yeah,
It's
yeah.
pretty much an outline of the thesis. But I just want to take a step back and take a look at that for 1 second, and then I'll let Loyd have the stage. But I just think that it really emphasizes, first of all, his enthusiasm for describing the work that he's done. I think it emphasizes his breadth. I think it's very unusual to have something that's going to cover as many topics as what he will cover. And I think it emphasizes his creativity. And so with that, I would like to turn this defense over to Loyd.
Now I gotta awkwardly switch over the that should do it. Okay. Well, thank you very much, Janet. And thank you everybody for coming. For those of you who know me for a long time, and there's a lot of you out there, this has been a dream for me for a long time. I applied to MIT 4 times before getting in. So it's kind of surreal for me to be here right now. So thank you. I'm going to go through all that, and I'm going to go through a little bit slower. I'm going to talk about how I can connect beyond the standard model physics, computation, and medical applications, and what each of these things mean, and how it's all done through high power cyclotrons. So one question. Oh boy, technical difficulty. I guess I'll do it the old-fashioned way. One question I get a lot is, what do I do for work? And a lot of the time, to be honest, I'm not always sure how to answer that because there's such a broad mix of different things. Sometimes I just tell people I work at a bar, but other times my kind of knee-jerk reaction is I do particle physics, right? I focus a lot on neutrinos. I'll talk to people about the standard model and how great it is, and also its limitations and how we're able to address them. And so sometimes people's eyes will glaze over, and then they'll be like, "Oh, is that like dark matter?" I said, not really. But I work on that too, by coincidence. I do some work on axions, which is a theoretical dark matter particle, and how we can interface this with our experiment. But what I really do most of the time is actually something called accelerator physics, where I'm doing a lot of design of electrodes, of magnets. I'm doing CAD models, I'm doing COMSOL models, and all kinds of different tools. And so what that means is most of the time, what I'm really actually doing is computational physics. A lot of writing code in Python, a lot of C++ compiling, and even some machine learning in order to make sure that we can get the most out of these designs that we possibly can and do the best kind of optimizations that we can. But when I'm trying to really elevator pitch someone, I'm trying to tell someone how cool what I really do for work is, I'll always talk about medical isotopes. I'll talk about how using this kind of technology, we're able to actually bring down the costs of things like cancer treatment and therapeutics down to orders of magnitude less than what they cost now. And the reality is I can work on all of these things at the same time because I work on the ISODAR project. Because what's really cool about ISODAR is even though it's a fundamental physics experiment at its core, it's actually able to touch all of these individual pieces and do so in a really cohesive way that I can talk about in my thesis. So this is going to double as my outline. So I'm going to talk about the original motivations in terms of neutrino physics and why we're actually looking at this. I'll talk about how we're able to kind of make sure that this works with the accelerator physics and the machine learning that we did to optimize that accelerator physics design. And then I'm going to talk about the more broader applications that have to do with axions and medical isotope development that we can use with this machine. So to understand the motivation behind ISODAR, you have to have a good understanding of neutrino physics. So a kind of fun, kind of goofy fact that a lot of people will give, or that our collaborator Josh Spitz originally found, is that neutrinos actually outnumber our normal matter, electrons, protons, and neutrons by 10 orders of magnitude. That's 10 to the power of 10. And you would think, well, we should be bumping into these things all the time, right? If there's so many neutrinos, why don't I see them? Where are they? Well, the reason you don't see them is because they interact very weakly. And when I say weakly, I don't just mean figuratively. I literally mean via the weak force, via the W boson. And so what this means, as you can see in this Feynman diagram here, say you have some neutron, it can decay over time and undergo something called beta decay, where the neutron will decay into a proton, emit this W boson, and then emit an electron and an anti-electron neutrino. But something that's really cool about neutrinos is that actually they oscillate back and forth. Their mass and their flavor eigenstates, their detectable eigenstates are not simultaneous. So say I have this source over here, which may or may not be ISODAR, and it produces anti-electron neutrinos, and I throw them to Janet over there, and Janet has a detector, and she looks in the detector and she says, well, this isn't an electron type neutrino. This is a muon type neutrino or a tau type neutrino. And that happens because there is some probability that they will actually change from one type to another, depending on the distance between the detector and the source and the energy that they're at. And this is a highly successful model that's won the Nobel Prize in 2015 for describing these different oscillations as they are able to change from one type to another. But since then, there's actually been a large number of anomalies, things that don't actually fit this model super well. Starting with LS&D in 2001, there was a low energy excess that was found in terms of these neutrino-like events. But this has been repeated in multiple different types of experiments. You can, mini boon being kind of notorious, but a little controversial, but there was also radioactive source experiments. There's problems in the reactor space. One in particular that I think really spells it out is this 5 MeV bump. So what this plot here shows is the predicted rate using Monte Carlo compared to the experimental rate. And if you take that in a ratio, it should be 1, right? You should have a perfect match of what your expected rate and your experimental rate is. And that would be just a nice flat gray line, right? This isn't a flat line. There's a lot of structure here. There's a big wave, there's a big bump. Some people look at the wave over here, and some people even say there's a little bit of an oscillation over there. But the bottom line is something is wrong with these predictions. Either we don't have a good understanding of what's going on inside the nuclear reactors. It's either that there's some kind of complex model that needs to be put into the nuclear reactors, or there's some kind of new neutrino physics going on here that we don't actually predict. And ISODAR addresses both of these constraints actually, the type of experiment that it's looking at. But what's something that we can look at and try and explain all of these different anomalies simultaneously? Well, as you saw in the video, this is actually called a sterile neutrino. But what I didn't go into too much depth in the video is, as more statistics have been coming out, it's starting to become more and more feasible that some of the more strongly theoretically motivated groups is that there's not actually a single sterile neutrino, but multiple. And this makes sense, right? You look at the standard model, you have 3 generations of everything. You have 3 generations of leptons, you have 3 generations of quarks. And so it would make sense that this would fit that same kind of structure, kind of intuitively. But once you start to get more sterile neutrinos, you also get heavy sterile neutrinos. And once you have heavier particles, the standard model tells us heavy particles decay. So these are all different parameters that you need to be able to fit, because as there are more different types of these particles, some of them are going to break down, and these are all different types of parameters that you're going to need to fit when you actually try and evaluate this type of model. So this is where ISODAR comes in. ISODAR is this neutrino floodlight, right? It's this isotropic anti-electron neutrino source that can easily be turned on and off, so you can get a good idea of the background. So say you want to just get a pure idea of any kind of radiation that's coming out of the rock. There's a small electrode that's about this big that you put to 4.5 kilovolts, and it stops the beam right at the beginning, so that the entire system can be turned off. And on top of that, it's actually put in close proximity to the detector. So here's a CAD rendering of that. We have our cyclotron on the left that sends beam all the way down to our target. And this is a 2.2 kiloton detector. This is set to be put in a mine in South Korea, the Yemi mine. Kind of zoomed in, what this looks like here is you have our cyclotron and RFQ dip, and I'll talk about each of these pieces individually. Sends beam to our target. The target has a beryllium cover. When the beam hits the beryllium, it produces a large amount of neutrons. The neutrons are absorbed by lithium-7, which are in the sleeve. Lithium-7 turns to lithium-8. The lithium-8 then beta decays via that same Feynman diagram that I showed in the very beginning, producing a large amount of anti-electron neutrinos. So we can do all kinds of neutrino physics that we're interested in. And this is starting to look less and less like an ideal situation, more like a reality, because we actually have excavation done. We've talked to our collaborators over in South Korea, and they've done the excavation complete with for the LSE, the large detector, and we also have a home for our cyclotron, a small cavern that's been dug out. So what is kind of the physics implications of this? Well, my group has worked on these things called global fits, which is when you take all of these different anomalies and you put them together and you're trying to describe what is the sterile neutrino going to look like? Where in this parameter space is it that we should look for? And if you couple ISODAR at Yemi Lab, you'll get this blue line. Everything to the right of this blue line will be excluded at 5 sigma. And for people who aren't familiar with what sigma means, it means, I looked this up last night, it's 99.9999, that's 4 nines, 4% confidence level over this entire space. So we're able to get, because we have such large statistics, we have 2 million inverse beta decay events, which are our detector events. and able to exclude massive regions that have a very big impact on neutrino physics. But what's more important is, in addition to this 3+1 model, this is the only experiment that I'm aware of that's also looking to probe not only a 3+1, but a 3+2, and a 3+1 plus decay. These are these additional models that I talked about earlier, because now we're able to get high enough statistics that we can actually properly evaluate these ideas, rather than just trying to fit a 3+1 and kind of do dances around that. So this is great. This has a lot of great physics implications, but why hasn't it been done yet? Well, if you want to have an intense neutrino source, you need to have an intense proton source. And that's where it starts to get tough, because you need 10 milliamps of beam current. But if you have a nice linear accelerator, that's not really a big deal. But the thing is, we're building this in a mine underground in Korea, so then we need to do it at a reasonable cost. So a nice linear accelerator isn't really going to fly. But if you want to do a cyclotron, which is kind of what you're stuck with in that footprint, that's actually 10 times higher than what's commercially available. So we kind of had to reinvent the wheel a little bit and do a fully new cyclotron design, this new isotope cyclotron. And how we're doing this, we're not just doing this kind of iterative approach where we're slowly starting to get better and tuning our beam dynamic simulations till 4 in the morning. I do that sometimes, but not in this case. We're taking advantage of these 3 breakthroughs to higher current. The first being the use of H2+, the second being designing for an effect called vortex motion, and the third being RFQ direct injection. And I'm going to take a step through what each of these things mean and how they affect our beam dynamics. So first is the use of H2+. This is actually a relatively intuitive part of the 3. So typically in a cyclotron, you have H- ions being accelerated. So when you have a beam, you have this cluster of all these ions together, and like charges repel, so they're all going to want to push apart. So this makes your beam start to deteriorate because it's getting way too big and it's hard to control, and you'll end up with problems. So what we do with H2+ is we're actually able to get 2 units of current for the price of 1, right? Because you now have these 2 bound protons bound to an electron. And then at the end, you can essentially double your current by using a stripping foil that removes the electron, and now you have twice as much current in terms of protons. And so you're able to transport a beam that has lower space charge effects, but also be able to get just as much current as what you need. And on top of that, actually, H2+ is more rigid than H- ion, so it's less likely to fall apart inside the cyclotron. Second is an effect called vortex motion, which can be a little bit tricky sometimes, but I have this going through in steps, so I think I have a pretty good explanation of it. So you have your beam, right? Your beam is a ensemble of particles that might exist in a bunch. And as I mentioned before, you have space charge, and the space charge is pushing the beam apart. It's making it kind of spread out. But remember, you're still in a cyclotron. And because you're still in a cyclotron, you're still in the presence of a magnetic field. Since you're still in the presence of a magnetic field, you can do your right-hand rule and you can say, well, this is going to exert a torque in that direction, which is going to cause the beam to not just follow its typical trajectory, but it's actually going to spin. It's going to form this vortex. And so what this looks like is in the case where on the left, you have a case where there is no space charge in our simulation. And on the right, you have a case where there is space charge. You can see they're actually quite different. They're making much different effects. And the kind of final punchline of this is that your final extraction is going to be much cleaner if you're able to design for vortex motion. And why this is so important, as you can imagine, going through the actual cyclotron, you have these things called collimators. And these collimators clean up the edges of the beam to make sure that you're only getting this nice round extraction system, or this nice round extraction in your beam. And this is kind of a profile of the beam that's going to be lost in those collimators. You can see there's not a very clean extraction here. You get a lot of cut and you don't have a nice round circle, whereas here you have a nice round beam that's going to limit any kind of radiation that's going to occur inside of the cyclotron. The next is the RFQ direct injection system. So typically, when we're talking about a cyclotron and we're talking about injecting beam into it, there's either an internal ion source where the ions are just camping out inside the cyclotron, and then the ions can be accelerated later. But that doesn't work for the type of ion source that we have. So normally we would be considered using a Levitt, which is a series of individual magnets that are directly injected into the cyclotron. But we're going to be using something called an RFQ. And the reason why is because when you do this, it's kind of like putting a fire hose into the cyclotron. So you can imagine that the cyclotron is actually only able to accelerate things within a certain time frame. So you can imagine kind of a conveyor belt filled with buckets, right? And in this conveyor belt, you're trying to fill up each bucket, and you're doing it with a fire hose. This is our direct injection beam. But what happens is as this is moving, you now have this getting dumped in between, right? You have a lot of losses here. But what the RFQ does is it bunches each of these pieces into individual bunches so that you can fill each RF bucket up. And so you have a high transmission of your beam without any losses, without any water dripping between the sides of the bucket. And on top of that, it actually makes the system much more compact. Rather than having this large series of magnets, you now have this RFQ direct injection system, which takes up a much smaller footprint, which is really important when you're trying to fit everything down in an underground mine in Korea. So what does this look like? This is the kind of system overview. And it starts with our ion source, which produces our H2+ ions. And then the next part is this Levitt system, this low energy beam transport that actually injects it into the RFQ to make sure that the beam dynamics are properly tuned, to make sure that it's able to get that high transmission, that bunching efficiency in the RFQ. And then of course, there's the RFQ itself. So starting from the beginning of the beam, we have the MIST-1 ion source. It's called MIST because it's a multi-cusp ion source. And what that means is you have all of these different magnets surrounding it, and that confines the plasma inside. So you have a filament that produces a large number of electrons as you put this current through, and that ionizes the gas chamber inside. And then each of these cusps help push the plasma towards the center, so the plasma can drift out of this central tube and out towards the electrode system. And we tested this and commissioned this at our lab down at PSFC, and we were able to show that it had an 80% H2+ purity ratio, which is great, and a very low emittance of 0.05 pi millimeters per milliradian. And as this goes to the Levitt, this can actually increase a bit, but it's in terms of beam quality, this is a very strong result. And as we're upgrading our Levitt, which I'll talk about next, we'll be able to get it up to full power and maintain that same ion source ratio. The next piece is this electrode Levitt. Now, there's a large number of constraints here that are basically describing making sure that it's properly injected into the RFQ. So you need to make sure you have the right diagnostic equipment, things to tune the beam dynamics, things to make sure that it's safe and that you can turn it off without actually damaging anything. And this might not be the sexiest part of my thesis, but this was by far the most amount of work and probably the hardest part, to make sure each of these individual design constraints were able to fit in. And while fitting each of these design constraints in took a long time, I'm going to try and condense it into 3 slides and just kind of skip to the punchline. And the punchline is basically that we were able to fit all these design constraints. We have a full CAD model, full rendering. The parts are being ordered and we're beginning assembling now. And this makes sure that we have a chopping electrode to dump the beam onto. We have all these diagnostic tools like an ACCT and the button pickups. We have a solenoid that we've designed to make sure that we can properly have another knob to turn into the RFQ. We have an additional cross for any kind of diagnostics like a camera or something like that. So there's a bunch of things that we added onto this in a pretty small region to make sure that we're able to have a nice, clean Levitt output. And on top of that, we have the beam dynamics, which are all properly tuned to make sure that we have a high transmission through the RFQ. In fact, our subcontractor, Bevatech, who has been designing this RFQ, gave us a set of parameters that they wanted the beam to look like. And this is on the right here. But with this design, I was actually able to get the emittance, which is this quality of beam, about a factor of 2 higher than what they had been using as their kind of optimum situation. And so we were able to get a very high quality beam in a region of accelerator parameters that ensures transmission of over 95%. So I feel very confident in the strength of this Levitt design and how it works with the RFQ. We're also working to do this full commissioning piece. Unfortunately, I was hoping to have some commissioning results by the time of this thesis, but there were a lot of problems with fabrication and whatnot. But the pieces are starting to come together, and you can see at least the electrode system nice and assembled down in the lab. And that was a happy day for me to be able to put all the copper pieces together, so that we were able to have a nice setup with the beam. The next piece is the RFQ, the kind of the star of the show. Even though this is where a lot of the work happens early on, the RFQ really is the main focus. And so what is an RFQ? It's this electric quadrupole, which means you have these 4 vanes. You have 2 coming each way, right? And it has 3 major effects. It accelerates, it bunches, and it focuses. And primarily, we're looking at our bunching effects, as I talked about before, with our RF buckets. But these other pieces are also very important to make sure that the cyclotron is able to accept the beam. And typically, these are all built by hand using computationally expensive codes like ParmTech and RFQGen. And it takes a long time, but we live in the future. And in the future, everything's done by robots and everything's done by machine learning. And so we wanted to try and change this kind of design space. And so we worked with trying to replace a lot of this process and try and automate a lot of this process using machine learning. And people might have heard of machine learning or AI and whatnot in the news, and you might have heard of, you might have seen some scary plots with a bunch of nodes and arrows and whatnot. And I'm going to try and explain it using cats. So the metaphor I liked was that, so imagine someone in your family comes up to you and they say, Daddy, I want a cat. And you're like, well, what kind of cat do you want? And they say, I want a cute cat. And you say, okay, that's not really helpful at all. So what you do is you say, well, a cat is really computationally expensive. It takes a lot of time. It's a lot of effort. And how about we do this? How about I give you a whole bunch of fake cats? I make you a whole bunch of cat cakes, right? And then you decide which one is the cutest. And they say, okay. And with that, that's kind of what we did here. We have our high fidelity RFQ simulations, and we used neural networks and polynomial chaos expansions to create these surrogate models, these high fidelity, similar, but much less computationally expensive neural network models. And then we're able to optimize over that space and then confirm the fidelity with it later on while saving a lot of computation time. But unfortunately, like these pictures, this is not actually a piece of cake. So there are 3 cases of being able to do this that we looked at. The first is the photocell, which is just a very basic accelerator system where you have a focusing and defocusing case. This is more of a proof of concept to make sure that we were able to use neural networks to properly describe these ensembles of particles. The next was a simplified version of the RFQ. So imagine you have a single fixed RFQ, and then we're trying to decide what are the beam parameters that we're going to be putting in. What are we going to inject, and how can we optimize that? So essentially a Lebbet optimizer that we can use as a real-time tool. And the third is we throw everything but the kitchen sink in here. It's the full design, full autonomy of the RFQ, and trying to figure out if we can do a full optimization over the full RFQ design space to figure out exactly what we want and have it fully automated. So in terms of trying to optimize the Lebbet parameters, this was done very well. We actually had sub% level errors in our surrogate models here. And neural networks were able to outperform polynomial chaos expansions by a little bit in a plot that I'll show next. This is essentially because these simulations are so fast and clearly so accurate, we're able to use this as kind of a real-time commissioning tool once we start to finally commission our RFQ. So we've created a useful tool here to make sure that we can match our beam dynamics to our commissioning results. When we do the full RFQ optimization, it didn't perform quite as well. It still was able to perform in worst case, around the 10% level. And so we were able to actually eliminate large amounts of the design parameter space, even though it wasn't perfect. So we were still able to have a useful design tool when we were making the RFQ, but it still wasn't quite at the level that we were hoping for. Here's a table describing all of these results in summary. And you can see that neural networks typically outperform polynomial chaos expansions, which are another form of machine learning that aren't as widely used. And now I see why. And this work has been handed off to Josh Villarreal, who's been doing some amazing work on trying to do a more complete optimization of this design. So next I'm going to switch gears. I'm going to start, now that I've kind of demonstrated that ISODAR has this strong accelerator physics and computational physics background, I'm going to start talking about some of the applications, and I'm going to start by talking about axions. So what are axions? Well, there's this strange phenomenon in nuclear physics where there's something called the strong CP problem. In terms of the strong force, you would expect that there would be some amount of violation of CP or charge parity. But it's never been observed. And this is possible. There's this theta parameter in the Lagrangian that could potentially make it so that there is no CP violation. However, it seems unlikely. It's a bit of a fine-tuning problem that people call it. And so to answer this question, 2 people, Petchy and Quinn, were able to find, they proposed this symmetry breaking, the spontaneous symmetry breaking. And what Frank Wilczek and Steven Weinberg then later found is that if you have the symmetry breaking, it would create a new particle. And Frank Wilczek told me once when I asked him about this, that he was in the supermarket with his mother, and he looked up at the soap the Axion soap, and he said, well, I want to name a particle after that soap one day. And then he found this problem, and he said, this cleans up the strong CP problem. And so he said, I'm going to name this Axions. And so now we have a particle named after a soap called the Axion. And what got people very excited is at sufficiently low masses, these axions not only solve the strong CP problem, but also describe a possible description of constraining dark matter in astrophysics. For this talk, I'm going to be talking about masses around 1 MeV. So this isn't as much of an interest. People with dark matter, it's mostly focusing on solving the strong CP problem. So there's a whole bunch of experiments that are looking into this. Abracadabra, I'm sure some people in the audience might recognize. And they're constantly expanding, trying to look over more and more parameter space. This yellow band describes where the QCD axion space is. And this other space describes kind of more axion-like particles or things that can potentially explain dark matter or part of dark matter without being a specific candidate for the strong CP problem. And so where I'm looking is there's this stubborn space up top here, that little white space of unexcluded region that has been avoiding models for a very long time. And it's called the cosmological triangle. And I'll explain why Isodar might be able to actually sneak into this specific region using some of its kind of unique characteristics. To explain how a lot of these experiments work, there's a bunch of different ways that people have attacked this problem. But I think this kind of light shining through walls is the most intuitive. So what you're doing when you're establishing this axion is what you're really adding this standard model vortex of photon-photon axion. So if you want to have a lot of axions, you need a large light source. So typically people think of something like a laser or maybe something like an accelerator beam dump or something like that. And then you need to put it in a magnetic field so that you have that second photon vortex. And then you have photon-photon axion, and you shoot it at a wall. And I know this might be a shock to some people, but when you shoot a light at a wall, it doesn't go through. And so you have this absorber in between here. And because the light doesn't go through, but the axions have such a small cross-section, it's expected that the axions go through. And you can do the same process in reverse on the other side, where you put another large magnet on the other side, and then you can have it convert into a photon and then have a photon detector, which is being used. And so this is kind of the idea of if axions do have this provided vertex, how you can detect them using experimental apparatus. But you don't have to have a big magnet. You can actually do this in terms of on a much smaller scale, because atoms have magnetic fields. So you have some atom A, and then you can do this process called Primakov scattering, where some incoming photon can scatter off of a nucleus and then produce an axion. And these axions have mass, so they can also decay, and this produces a diphoton decay. And so it's the same process, again, just with atoms instead of using large magnets. So if you want to get a general description of this, you want to try and get a good idea of the number of events that you're going to be observing. We use this kind of general description in our paper that we submitted for axions. And this is really based on three major pieces. The amount of flux that you're getting for your axions. So how many axions are being produced in the source? How powerful is your beam? How powerful is your laser or whatever source you're using? The probability of it being detected. So this is going to have to do with the geometry of your detector. How much stuff are these axions going through? Are they going to scatter before they reach the detector? How big is your detector? Is it going to be able to actually be detected within the region of your detector? And then of course the energy threshold of your detector. You're not going to be able to detect axions that are too low energy. And what these really boil down to is cross-section, just like everything else in particle physics. They boil down to some cross-section or a branching ratio. And these are determined by their coupling constant and their mass. And so typically when we talk about axions in those plots that we showed earlier, I describe it on a plot that describes both the mass and the coupling constant. So what does this mean for Isodar? This seems like a pretty big tangent, but if you recall, Isodar is this nice neutrino source that has all kinds of crazy nuclear reactions going on because you have lots of protons running into a big target. And when you have all of these nuclear excitations, you don't just get neutrinos and you think, oh, wait a minute. I think when you have all of these interesting nuclear reactions, you'll actually get a large number of photons. And you think, oh, well, what can I do with a large number of photons? Well, I can see if these shine through walls. I can see if we have this Axion experiment that's actually going to be, we have this absorber, which is literally just cement that we're using for neutron shielding. We have all these photons and the nuclear reactions that are happening in the target. We have all these atoms that can act as a magnetic field. And fortunately, we also have a 2.2 kiloton detector with a bunch of other atoms in it surrounded by PMTs, which happens to be there very conveniently for us to be able to do this light shining through wall experiment again in a very different setting. And so if you look at our photon flux, which we found using J-on-4, and then you plug this into the equation that I described earlier on, you can then end up with some kind of Axion flux and make some kind of prediction about the exclusions you can make with these Axion particles. So using J-on-4, which is quite an experience, we were able to separate each of these kind of atomic resonances. And one thing that's really unique about ISODAR that makes it special and makes it able to compete with these larger, higher energy experiments is that we have these monoenergetic peaks. And you can see it here broken down by each individual atom that is being excited. And because we have these nice sharp signals that would normally get washed out when you have a much higher energy beam, like something at CERN or something like that, we're able to look for these sharp peaks and actually get competitive limits with some of these much larger, much more expensive projects. And not only that, but in terms of when we were going through the J-on simulations, we actually were able to find that there's a reasonably large electron and positron flux. And some of the other Axion models not only couple to photons, but couple to nucleons and couple to these electron and positrons. And each of these are, in the case of photons, it's actually isotropic because it's being dominated by these nuclear excitations. You're able to get a nice isotropic signal rather than having some kind of directional dependence. And so this unlocks even more Feynman diagrams that we can look at and even more models that we can exclude for axions. And so simultaneously while doing our neutrino search, we're actually able to do multiple different studies at the same time. So we're able to look at our typical Primakov scattering that I described at first, but also looking at axion couplings to electrons and axion couplings to nucleons. And doing all of this actually above the neutrino background or the electron-like neutrino event background that we have from our typical neutrino source. And so what do we get for results? Well, the Primakov scattering results is actually the least exciting out of it. We get a little tiny bit of space here and maybe a little bit on the QCD axion space here. But we're also able to confirm some astrophysical constraints. But a lot of this you can say is, well, the fact that we're able to keep up with a lot of these larger experiments, I think is kind of impressive in itself, and confirm those. But if you look at some of the other models, like the electron, for example, you're able actually to exclude certain amounts of the QCD axion space that haven't been looked at before. And this is coupling with purely electron-like effects, which is that second row of Feynman diagrams that I gave on the last slide. Then if you try to mix and match some of these, you can get a large, because you have all of these nuclear excitations, you can actually get a larger axion flux from the production of axions in the target from these nuclear effects. And then when you detect them using Primakov scattering, we can actually get an order of magnitude more space on the exclusion limits of this parameter space. And you can do the same thing when instead of mixing and matching with nucleons and photons, you can mix and match nucleons and electron scattering, and you can actually get a little bit of QCD axion space up there in addition to this large region we're able to exclude. So we have this new technology, right? We have this, say we have this ISODAR cyclotron that's able to have a compact high current beam. Well, most cyclotrons are not actually used for particle physics. I'm not aware of any cyclotrons used for particle physics, but there's still a lot of cyclotrons out there. The IBA C30 and the C70, for example, those are some competitors that we've looked with and talked to. And we're in kind of the same ballpark as their higher energy machines, but have much higher current. So what are these used for? What makes these so commercially viable? And the answer to that is actually medical isotopes, right? So you go to the doctor, you go and get a PET scan, right? This is how they're produced. How medical isotopes are actually used is it starts in this region that most people don't see. It's accelerators are shooting a proton beam at some target. The target then produces these radioactive isotopes that are then extracted through nuclear chemistry processes and then sent to a hospital. That hospital then takes it and injects it into you. And then in the case of therapy or some PET scans, it actually attaches itself to an unhealthy cell using some ligand or glucose or something like that, and then radioactively decays and can kill the cell or provide some kind of diagnostic treatment like a positron emission. And so when you're actually in the hospital, what does this look like? Well, it looks like someone on a computer actually seeing what's going on. So there's a little bit of a caveat with this. When you have the isodar cyclotron, it's 600 kilowatts, which is a pretty high power beam. If you try and put this on any kind of medical isotope target, it's going to explode. It's going to melt. There's way too much power in any of these beams. However, the good thing about the isodar cyclotron is that not only is it just producing protons like most H- type cyclotrons are, but it's extracting H2+. And this means you can actually break off the beam pretty easily using just a dipole and a stripping foil. When you remove one of the electrons, and then you can bend the protons off because the protons now have a different charge to mass ratio than the H2+ does. And then you can have multiple different target stations. So you can do this over and over and over and over again. And so you can, instead of having this one super high power target, you can have a bunch of smaller targets. And you can use this as a test bed to try and fight off this limit that you have all these low power targets. That's an area that really needs research and development, because you can variably change the amount of power on target while simultaneously using it for industrial applications like medical isotopes or even some nuclear physics experiments. So what are some of these isotopes and why are they so exciting? Well, I think the most exciting one that I've seen is actinium-225. So this was a group in 2014 to 2015 that used a therapeutic agent of actinium-225. It emits 4 alpha particles. This kills everything within a 50 micrometer radius. And so what you're able to do is you attach it to some ligand. The ligand attaches itself to a tumor, just like the picture I showed, and then kills it within that small region. And you can see this picture in the black is a PET scan where all these black spots are tumors, right? This person is a dead man walking, and this is probably why they were accepted into a clinical trial. But what the amazing thing is, within 9 months, actinium-225 was able to clear this up. And so, like, why isn't this on the news all the time? Why is this not being used by everyone? Well, it's really expensive, and it's being produced in very small quantities, predominantly by DOE and by a couple of smaller commercial entities. And they have relatively low beam power. While I'm talking about 10 milliamps, they're using about 100 microamps. And back in 2012, they were looking to increase the world supply by 60 times using this 100 microamps. They haven't really upgraded their facilities in this case. They've upgraded their targets to be able to handle more, but it's still very slow. They're looking to try and get 2 to 3 curies a year, even with their more updated estimates. And if we're able to use this full power of the isodar cyclotron, like I said, using those different target stations and breaking it off, we're able to get 200 millicuries per hour. It's a huge change that could really bring down the cost of this, because right now I did an estimate once, and it was something like $500,000 per treatment, which I can't afford if I got cancer. So another thing that we could look at is using PET isotopes. So on the left, some people, if they pay attention to nuclear medicine, they might have heard of something called the Moly-99 shortage, which is this spec isotope. So you have an isotope, it attaches itself to a tumor, and then it emits a gamma ray. And this is starting to slowly be replaced by PET scans. And you can see why, because there's a large number of tumors that would have been missed if it was only done using a spec scan instead of a PET scan. And the reason why PET is taking so long is, again, because of cost. These scanners are much more expensive than a typical spec scanner is. But these costs are starting to come down. And as the cost of the scanners go down, the demand for these isotopes is going to go up. And so again, you're going to run into a shortage problem. And so what Isodar is able to do is using, again, if we were to have an estimate where we have the full power of the Isodar cyclotron producing solely gallium and germanium, we're able to produce 50 curies of the gallium parent a week. And then this gallium can be shipped to a hospital. It's then milked to produce the germanium-68. And the germanium is then used as a PET isotope. And so this can eliminate a lot of the rapid supply chain problems that happen with Moly-99, because you're able to stick with this much longer half-life parent, you get a much higher resolution scan. And so it's a real win all around with something like this. Something else that would be interesting is, what if you could do both of these at the same time? What if you could simultaneously look to see how the tumors are progressing with the same type of ligand attached to it as you do with actinium-225? So you can do both diagnostics and therapy and call it something, I don't know, like theranostics, right? Well, we can do this. This is an isotope called cerium-134. It attaches, it's chemically very similar to actinium-225, and so you can use it to attach to the same type of ligand. So you can simultaneously do this therapy. This is an image from Department of Energy when they had started testing cerium-134, and are able to show that you can do this simultaneous testing. And using Isodar and breaking it off into different stations, you could have this kind of one-stop shop to do all of it at once, to produce all of it at once. Something cool about Isodar, though, is that with some minor tuning changes, we can actually accelerate any ion that has a charge mass ratio of 2. So that includes alpha particles and even carbon-6 plus. And when I heard carbon-6 plus, I thought that was a little crazy, but there are commercially available ion sources for it. Here's one of them from Pantechnic. And so because it's 60 MeV per nucleon, we can actually get much higher energy interactions with this. And so we're looking to try and unlock new reactions using these different types of ions in these higher energy fields. So kind of in closing, here's this layout that I gave at the beginning. Here's the kind of journey that I've been on with talking about neutrino physics, accelerator physics, and how this all blends together with all of these different pieces. But don't take my word for it. You can actually find all of these papers online. I have a paper for each of these, and most of the time I have a couple. You can, I don't know, if the mood strikes you, you can pick up a paper, grab a beer, and kick back. And what better place to do that than at 24 Lexington Avenue in Gloucester at JD and Myers. Feel free to read all of those papers or ask me if you're interested in them. So the last thing I need to talk about is the acknowledgments. This is really a group effort. I'm so grateful to everyone in this room. And I need to start by thanking Janet and my committee. Mike and Lindley, you also taught some of the best classes that I had here. So I wanted to say I appreciated that. Janet brought me in and brought me into a wonderful group with so many great people. Nick and Josh helped set up the room today. Joe was my lab partner for years. Jose has taught me so many different things about just kind of the world as a whole. And Daniel Winkliner, of course, has held my hand through all of the stupid coding mistakes I've made and taught me through all of the things when I felt really foolish. So thank you to everybody in my group. I also need to thank my family for supporting me through all of these years. My dad, my mom, and my uncle, Artie. Artie, even though he's not blood related to me, he's the one person in my life that I've really been able to count on. When things hit the fan, he was always there, and I really appreciate it. I also wanted to say we have an awesome staff at MIT. Our admin staff, and yeah, Joe Cusinato's a ghost. I couldn't find him anywhere. I get on the phone with an insurance company and talk to their admin staff, or an HVAC company to talk to their facilities people, and it will ruin my whole day. Like, it is a nightmare. And so the fact that we not only have staff that will help you, but will go out of their way and say, oh, here's this thing that is super helpful, you might be interested in it, is amazing. So I'm really thankful to a lot of the MIT staff here, because they really are taking a step above and make it more than a kind of professorship. I also want to thank my friends from home who are in the back. I really think I have some of the best friends in the world. I'm 27 years old, and I can say I have the same friends for 20 years. I want to draw special attention to this picture, right? So we took this picture because we had played football together since we were 7 years old, right? And this was our senior year. We had played football together for 10 years. And those guys are still in the back right now. This picture is 10 years old this Thanksgiving. And so, I mean, they've been awesome. I have an awesome girlfriend, Janelle, who's been supportive through all of this. And so thank you guys for coming. You guys have always been so supportive in every way. I also have a lot of great friends in LNS. I think one of the most special things about MIT is the people here. So, I mean, the education is great, but I mean, to be blunt, a lot of the time you can find it on open courseware. It's all there, right? It's all there, and it's all for free. But what makes it different is I can go and I can knock on Brandon's door and I can ask him a question, or I can run over to the CTP and it will bother them if they don't know the answer, and they will just they will fill everything with chalk and explain everything to me in such fine detail in such a humble way that, like, that's the only way I go through it sometimes. And I mean, Field and Kiara and Greg and of course Brandon, who's in the back, have been like, that is where I've done so much of my learning, is not just in problem sets and in lectures, but literally just like talking to these guys and learning so much on an individual level, which is super special to me. I also need to thank the Zapiens group, who helped me meet a ton of really awesome people. And not only that, but like Josh and Tom in particular, and Bobby have also kind of changed the way that I'm able to really look and approach problems. They're able to kind of help me break down individual pieces and figure out the right way to think and approach these issues. Another group that I gotta attend to is my Curio. Oh, the video didn't load. Oh, that makes sense. So there's a group of us that went to karaoke pretty religiously every Thursday. And I was scared to sing the first time. But to those of you who went to the LNS seminar a couple of years ago, I've turned into a bit of a diva. So that's been a big part of my MIT career as well. The last person I want to thank is a little bit less obvious and not as directly related to my thesis work. But if you look back at my life and my career, there's a single inflection point. There's a single time where I met someone that really changed my life, and that was the day I met JP Lane. But when I met JP, I wasn't sure I was going to be a physicist anymore. I was struggling in my classes. I was nervous. I wasn't even going to graduate. But I love Draper, and I went in and I felt like I was in the Avengers. And I sat down with JP, and it was before the atrium. It was this crappy little lobby with a table that was like this high and these little kid chairs that we had to sit in. And and I handed him my resume, and he looks over it and he nods. He says, "Oh yes, this is fantastic. I can't say this because of HR and whatnot, but between you and me, you have the job. Do you have any questions?" And I'm sitting there like, are you sure? is that what's happening? And so I'm reeling. I'm thinking, what can I ask this guy? Because he just offered me a job, and I can't just stand here dumbstruck. And so I said, "What about this Draper Fellow program? How's this going to work?" I said, "Well, you work here for a year, then we'll connect you up with some people in the Draper Fellow program, and then we'll get you into MIT, and you'll have a full scholarship and everything." This guy's out of his mind. I have like he's insane. How am I going to say this? I say, yes, that sounds great. And even though I didn't believe it at the time, he was right, and I can't believe it. He's here with me now, and I'm so grateful to have met you, JP. So thank you. And so that's it. If anyone has any questions, this is the conclusion of my presentation.
But now we need to actually move it back to the physics.
Yeah.
So are there questions on this result?
Yeah.
For the Axion,
Yeah. Mhm. Mhm.
Because there was that like small region on it to the temperature.
Yes. Mhm.
Why was that so difficult?
So I would make the argument that it's a pretty small region overall. But here we are. And so there's very high energy beam dumps, but our advantage is that we're able to have these sharp peaks, which is not possible with higher energy beam dumps. And so we're able to just get kind of iteratively better just by having sharper peaks. I mean, you can keep going, you can keep having higher energies that can more fully exclude that. But that's just kind of where it is right now. Yeah.
Are there other questions?
I do that by handing it off to the biophysics people, and then they handle it. I think there actually is a lot of engineering that goes into that. So one common one that I've heard, there's two common ones I've heard. I've heard some that are actually attached to neurotransmitter sites, which kind of scares me, but I guess that's how they do it. And another one is just like raw glucose. And so tumors will tend to eat up more glucose than everything else around it. And so if you attach it to some kind of glucose similar substance, it'll get eaten up by the tumor and then decay there.
Actually talked about when you can dual molecules,
Yeah, the theranostics. Yeah.
Yeah, and so it's a good question, right? So how do you know where it went? One of the things you can do is you can take a theranostic pair, and it will behave exactly the same way clinically as what you're putting in. So at least you can see where that went, right?
Right.
But you're right on the right question.
Yeah. Because that is a real problem, right? Because if, say, whatever ligand you're attaching to isn't going to the tumor, it's going into like my hand, and all of a sudden I lose control of my hand because I've put radiation in my hand, right? Now you can know with having this theranostic pair. Yeah.
Any other questions? Okay, if not, then what happens next is we go into the closed session of this. So you all will be asked to